So welcome back to BioMindscape. Today we are going to know about the Lotka-Volterra model. So Lotka-Volterra model is of interspecific competition. Now what is this interspecific competition? For example, these are the two species. We have taken two different species. So these both species 1 and species 2, they are competing for the food or nesting, like birds are building their nest. So they are competing with each other or building. That is interspecific. And intraspecific competition is between the two similar species of same species competing with one another, that is intraspecific. So we know that what is interspecific and intraspecific. So now let's know about the Lotka-Volterra model. So this was found by two different physics and mathematicians. It is a mathematical equation. We are going to know about the Lotka-Volterra model. So the Lotka and Volterra, they independently find out about the interaction. The mathematical model, it was developed by two different people, and they work independently. So Alfred Lotka in 1925, he found Alfred Lotka, and insurance accuracy, and Volterra in 1926. These are the years in which he was a mathematician and physicist. So on the basis of this model, the loser of the competitive interaction can be predicted. So Lotka-Volterra equation for interspecific competition is based on the Walsh-Pearl logistic growth equation. So what is the Walsh-Pearl logistic growth equation? That is somewhat like dn by dt is equal to Rn in bracket k minus n upon k. This is the equation, and this is a logistic equation. A rate of population growth is limited by interspecific competition, member of a same species that are competing with one another. This equation can be modified to include the effect of interspecific competition as well as the interspecific competition. So Lotka-Volterra model, it was developed to allow the various ecologists so they can predict the outcome of two different species that are competing for the same resources. So basically this model attempts to account for the effect that present one species will have on the population growth, and what will be the effect on the other species, and relative to the competitive effect that the two members of the same species would have on each other. So the logistic growth equation for Lotka-Volterra model for two species, like species 1 and species 2. So the logistic equation for growth 1 alone is, we will know that logistic growth equation dn by dt, it will give r1n bracket k1 minus n1 upon k1. So this is the for species 1, and Lotka-Volterra equation for species 1 in presence of species 2, it will be represented as follows. So it will be like dn by dt will give r1 n1, then in bracket k1 minus n1, then minus alpha 1 to n, that is alpha 12 upon k1. So this will be where n represent the negative effect of intraspecific competition of logistic growth, and k1 represent the negative effect of interspecific logistic growth. So the logistic equation for species 2 will be like, let's note down the second equation for species 2. So for species 2, the equation will be dn by dt is equal to r to n to n bracket k2 minus n2 minus alpha to 1 n1 whole upon k2. For species 2 it will be like this. So where n1 and n2 are the population of species 1 and species 2, and so I am writing it down. So n1 and n2 are the population of species 1 and species 2 respectively. K1 and K2 they are the carrying capacity of the system for each species in absence of the other, and T is the time. R1 and R2 are the intrinsic rate of increasing species 1 and species 2 respectively. Alpha 12 is a competition coefficient representing the effect of one individual of a species to grow of species 1. The first number of the subscript always refer to the species belonging to the affected one, and alpha 21 is a competition coefficient representing the effect of one individual of species 1 on the growth of species 2. So the competition coefficient is a constant quantification of the negative effect of an individual or species on a population growth of other species. Now what does this means? So competition coefficient, it is a constant. So what does it quantify? The negative effect of an individual on a species on a population growth of the other. So both the population are depending on each other. So the value of competition coefficient is the ratio of the competitive effect of each species. For example, if one species is there, so one individual of species is given, it has the same competitive effect on the population level of species 1 as 10th individual of the species 2. Then the competition coefficient would be 1 by 10 is equal to 0.1. So we will know this line. So now we are going to know about this competition coefficient. So competition coefficient, it is always represented by alpha. So it tells us how much one species affect the growth of the another species if we compare it to the effect of its own member. So for example, if species 2 individual is there, this is species 2. So individual, it reduces the growth of the species 1. This will reduce the growth of species 1, and the strength of the effect is given by alpha 12. So similarly, if species 1 individual affect species 2, then it will be alpha 21. If this effect on the species, similarly if species 1 is going to be affecting on the species 2, then it is alpha 21. Whereas if species 2 is going to affect on species 1, then it is will be 12. Like 2 affecting on 1, so it will be alpha 12, and 1 will be affecting on 2, so alpha 21. So this is the easy way we can remember. So alpha 21 is the effect of species 2 on species 1, and alpha 21 is the effect of species 1 on species 2. So how we will measure? It is it's a ratio. So if one individual of species 2 reduces the growth, species 1's growth as much as 10 individual, like alpha 21, alpha 12, that is 2 by 1 here. So what will be the next step? So alpha 21 is equal to 1 by 10. That means the one individual species of species 2 is reducing the species 1's growth as much as the 10 individual of the species 1. So 1 by 10, it will give 0.1. This means species 2 competes less stronger with species 1 if we compared it with species 1 to its own member. So this means species 2 competes less strongly with species 1 compared to its own member. So interpreting the alpha value, so if the alpha is greater than 1, so interspecific competition is weaker than intraspecific competition. Other species affect you less than your own member. So alpha, if greater than 1, so it is interspecific competition is stronger than the intraspecific competition. So the other species hurts you more than your own member do. So assuming if we assume it for Lotka Volterra model, So the growth rate and carrying capacity and the competition coefficients are constant. So every individual is identical with the species, no age size difference, and the population doesn't change genetically, so no evolution or diversification. So the habitat is homologous, uniform resources, and no spiral variation can be seen. So these are some of the assumptions of the Lotka-Volterra model, and why it is important, because Lotka-Volterra competition equation predicts whether the two species can coexist stably, or one species will outcompete and exclude the other one, or if they'll reach some balance depending on an alpha value and carrying capacity. So in short, the competition coefficient alpha measure how strongly individual of one species affect the growth of the another species population. So if alpha is greater than 1, so weak effect, the species can be more easily coexisting, where alpha if greater than 1, so the stronger effect, no one species likely to exclude the other. So now let's know about the Lotka-Volterra competition model. So there is an equation for this, that is dn by dt. dn1 for species 1, dn1 will be represented is equal to r1 n1. So r1 is the intrinsic growth rate and n1 is the population size of the species 1. So r1 and n1, and in bracket we will write here 1 minus n1 plus alpha 1 2 and n2 upon k1. So this is an equation for the species 1, whereas if we will just write dn2 upon dt is equal to r2 n2 in bracket 1 minus n2 plus alpha 21 n1 upon k2, that will be the equation for the second species. So now we will know 4 possible outcomes of this Lotka-Volterra competition model, in which we will first draw it and let's explain it. So first, this one, there are total 4 graphs. So one by one we will know if the species 2, if species 2 wins, then what will happen. So if species 2 wins, from top left, here the blue line lies outside the red line, so species 2 always outcompete the species 1. Eventually species 1 goes extinct and species 2 survive. For example, Paramecium aurelia, it outcompetes the Paramecium caudatum, like in Gauss experiment. Then species 1 if win, like in top right we can see the red line lies outside the blue line, so species 1 always outcompete species 2. Eventually species 2 goes extinct and species 1 will survive. Then unstable coexistence, in bottom left we can see the isocline cross, where which species win depends on the initial population size. If species 1 start with the high number, then species 1 will win, and if species 2 start with higher number, then species 2 will win. So this represent the priority effect. Stabilized coexistence is shown in the bottom right. So the isocline crosses in such a way that both the species regulate each other. So equilibrium point is stable population converge to coexistence, and coexistence occurs when interspecific competition is stronger than intraspecific competition. So example, species limit their own growth more than they limit each other. So this is ecological, the most realistic scenario for biodiversity.